AI is quietly moving into a more dangerous phase. Models are becoming better at using structure, but also easier to hide behavior inside. One result shows GraphRAG can recover from the text embedding mismatch that has made frozen LLMs stumble on graphs. Another shows eGraphs can finally treat context and variable scope as first-class citizens. And the third shows a backdoor can be statistically invisible even with white box access. The common thread is control over representation. Keep watching, because that's where the real leverage and the real risk is hiding. Let's explore the first paper, AG Adaptive Masking for Graph Embedding in Graph Retrieval Augmented Generation. AGE from Omron Corporation and Omron Cynic X Corporation targets a core failure mode in GraphRAG. Frozen LLMs cannot reliably consume graph embeddings because graph latent features drift away from text encoder spaces. The method replaces random node masking with an RL-trained node sampler that identifies key nodes and masks auxiliary nodes, then trains a transformer-based concept encoder-decoder with a JEPA objective to reconstruct auxiliary node representations from key nodes. This design is paired with a graph structure aggregator and a frozen Llama backbone, including Llama 3, 2.1b, 3b, Llama 3, 1.8b, and Llama 2, 7b, 13b. On Explay graphs, AGE lifts gRetriever from 0.5595 to 0.8267 with Llama 3, 2.1b, and ablations show the full JEPA plus node sampler stack beats GA and random masking, reaching a 26.72% improvement over baseline versus 9.37% and 15.46% for weaker variants. On WebQSP, AGG Retriever reaches 80.3 hit at 1 with Llama 3, 1.8b, LoRa, outperforming gRetriever's 70.2 and narrowing the gap to parametric retrievers such as Dual R at 82.8. The paper also reports that a sampling rate of 0.3 is the best overall trade-off and that AGE can preserve or improve accuracy while keeping training at 2 to 7.3 minutes per epoch and inference as high as 148.5 tokens per second. Let's explore the second paper, Lifting eGraphs. A function isn't a constant. Lifting eGraphs. A function isn't a constant proposes a lifting-aware extension of eGraphs that treats context as part of term identity, avoiding unsound variable capture while increasing sharing across differently scoped expressions. Built on ideas from slotted eGraphs and code-de-Broglie syntax, the paper represents lifted terms with fat identifiers that pair an integer class ID with a thinning bit vector, then uses lift-pulling smart constructors and a thinning-aware union find to canonicalize equalities under alpha equivalence-like context changes. The key technical move is to make lifting a first-class combinator. Lift compositions collapse by thinning composition. Lift homomorphisms push through function symbols, and union can peel common thinnings to recover ordinary equality, or synthesize a fresh representative when two lifted forms are not directly reconcilable. The result is an eGraph modulo theory style design that can compact expressions such as x, y, z, w, 7 to 42, plus 42 into a single pulled form, while preserving distinctions like sin1 and sin2 only up to their shared lifted structure. The paper also generalizes the same machinery to annotated union finds, including offset, monas, and factor variants, to show that group structure is not required for relational union find annotations. Let's explore the third paper, Statistically Undetectable Backdoors in Deep Neural Networks. Andrei Boganov, Alon Rosen, and Nikon Vafa show that a large class of deep feed-forward neural networks can hide a backdoor that is statistically undetectable even in the white box setting, meaning the backdoored and honest models are close in total variation distance despite full access to all weights. Their construction plants a secret vector z in the first frozen compressing Gaussian layer with a rejection sampled or conditionally sampled matrix. A satisfying Zaz infinity is approximately equal to O square root n2 n m, so the model owner can always create a colliding input, xs equals x plus z, that produces unusually close outputs, while an efficient outsider cannot find comparable collisions under standard lattice-based cryptographic assumptions. The main theorem proves that any efficient trainer for networks with a Gaussian first layer, by Lipschitz, downstream layers such as leaky ReLU, and discrete bounded inputs can be modified into a backdoor trainer with statistical deviation, s equals O square root m divided by n, and backdoor strength growing exponentially in the compression ratio n divided by m. They also show tightness up to logarithmic factors, with a distinguisher achieving sex, square root m, n advantage, and demonstrate a proof of concept on fashion MNIST, where a 784-256 embedding network reaches about 89% test accuracy, dropping to about 86.5% under the backdoor-induced distribution shift. That's a wrap on today's AI paper highlights. Thanks for watching.